leave your camera off. For technical support, contact Ulrika Örnemar, who is the one who invited you to this meeting. And if you have any questions and comments during the introduction or during the presentations, please share them with all of us in the chat. Questions will be answered during the panel Q&A session in the end of the meeting, and the questions will be posed by me anonymously. If you don't have time enough, remaining questions will be answered in written by the presenters, distributed to all of you and also posted on the HBT Annex 51 website along with the recording of the webinar. And please avoid to have a parallel discussion in the chat. So again, welcome to this webinar where the final results from HBT Annex 51 acoustic signatures of heat pumps will be presented. My name is Caroline Haglund Stigner and I work for the Heat Pump Center, and I will be the moderator for this webinar today. This is the agenda for the webinar. I will start with a short introduction, and thereafter you will get an overview of the Annex 51 project. After this, a number of presentations will follow, and as I said before, we will, in the end, we will have a panel Q&A session where questions from the chat will be answered. The HBT Annex 51 is an international collaboration project that has been performed within the IAA Technology Collaboration Program on Heat Pumping Technologies, HBT-TCP. So what is this? What is HBT-TCP? It is a technology collaboration program that has been going on within IAEA, the International Energy Agency, since 1978. It's a framework for international cooperation and networking for different actors that works in the field of heat pumping technologies. It's a forum to exchange knowledge and experience, and it contributes to technology improvements by performing different research, development, demonstration, and deployment projects. And today, the program has 17 member countries around the world. The countries marked with red in the map to the right. The program covers heat pumping technologies for heating and cooling, air conditioning, and refrigeration. It covers applications in residential and commercial buildings, industries, thermal grids, and in cities and communities and other applications. Within the program, a number of international collaboration projects are carried out, and this Annex 51 is one of them, and then you see a few other examples here. The Heat Pump Center is the communication center and program office for the HBT-TCP. We work a lot with information dissemination and communication through our different channels. We publish reports from annexes like this. We publish an electronic magazine, a newsletter 3 times a year. We run a website with a lot of information, and we are active on social media such as LinkedIn and Twitter. We do also work with program support in different ways. We support the board of the TCP, the executive committee, national teams, the projects leaders of the Annex, which we call operating agents, and so on. Now you will get an overview of the Annex 51 project. So I will stop sharing my screen, and Christoph Reichelt from IIT in Austria, the operating agent, will give this overview. And now we see your slides perfectly well, Christoph, so you can start. Christoph, please, you can start your presentation.
Open your mic.
So, I hope you can hear me.
Yes, we hear well.
Yes, that's good. So I'm just getting ready and let's go. So from my side, a very warm welcome here to the Annex 51 webinar. I will have some small slides in the beginning and then we go into the topic already. So it's a webinar about our final results. It's at some stages, the documents will be further updated in the next months. But in the end, it's a lot of stuff which we want to show and share with you. And what I will tell you now is some small introduction to the EAR HPT Annex 51, some documents you can find on the website for download, and then we go to the webinar content from today. So introducing Annex 51. It's a journey we have taken the last 3 years. We started with a kickoff meeting in Austria and then went through the different countries, meeting, discussing, and trying to get everything sorted out. You see some figures here from heat inside climate chambers, outside buildings. And then for reasons you know, we moved into World Wide Web and skipped Italy, which is a pity because we wanted to be at Mostar Convenio and share all this stuff there. But in the end, we are now online and I will not bother you too much with the legal text. And all these annexes have legal text, but one sentence is important for us. We want to increase the acceptance of heat pumps. And this is what we will try to do. And we have set up some tasks for that, and I will go through them a little bit here. It will be one about legislation and standards. We have a definition of heat pump units to be covered in our study and testings. We have a task about identification of noise at component and unit levels and noise control techniques. Then we had set up task 4 for the analysis of the effect of operating conditions of heat pumps on acoustic behavior. Task 5 about heat pump installation and effects on surrounding environment. And 2 last ones, one about improved measuring and description of the acoustic performance. And the last one is diffusion, dissemination of information, guidelines, education material, and recommendations for different user groups. And we have tried to bring all these together for today and have put it to our website. So if you go to the Annex 51 website in this heat pumping technologies part, then you will first of all see the content for today. You also have the possibility to download all the presentations you are seeing now. And then you have already the documents available, which we are speaking. And these are the deliverables of our tasks. And you see them here. It's the first is about a general introduction about measurement techniques, about regulations. And the second one is about selection of heat pumps for the round-robin tests. Then the round-robin tests described. And then about seasonal sound power level. And then we have an overview on heat pump component noise, the analysis of the effect of operating conditions, one report on the heat pump installation, and one report about the annoyance rating and psychoacoustic analysis of heat pumps. You additionally find on the homepage some presentations we have done at ICR 2019 and some national documents from the partners. And so this brings me to today's webinar content. We'll not see everything here, so we will miss task 3. The downloads papers are already there for you. We will focus on the following content, and this will be about European legislation and standards, about noise and seasonal variations based on interlaboratory results, the effect of different heat sinks and operation modes, transient noise of heat pumps, heat pump installation and effects on surrounding environment, and last but not least, annoyance rating and psychoacoustic analysis of heat pump sound. And you see the presenters here, and I will at this point give back to Caroline and ask her to introduce our first speaker. And thank you for your attention for this first part.
Well, thank you very much, Christoph. Our next speaker now, it is Roberto Fumagalli from Polimi in Italy, who will talk about European legislation and standards. And now we see your slides in the right mode, so please start your presentation. can please start your presentation. Roberto? Yes, please go on.
We can see your presentation, but don't hear you yet, I think.
Roberto? Yeah, we see your presentation, but we don't hear you. Now.
We have no sound from you.
Okay, it seems like there is a problem with the noise from Roberto, so I think we will try to solve that and go on with the next presentation by François Besac from CETIAT and Thomas Gindre from ICE in Germany about noise and season variation based on interlaboratory results. Could you please, François? Yes, now we see your presentation well, so could you please start your presentation?
Yes, thank you. So I'll speak about the noise and seasonal variations of heat pumps based on interlaboratory results. So I'm François Bessac from CETIAT, and I present this presentation with the support of Thomas Gindre from Fraunhofer. CETIAT was in charge and the leader of the task 2 for round-robin tests. These interborough heat pump measurements are done to compare the robustness of noise standards and laboratory implementation. It's very important for accredited laboratories to compare themselves, so it's a goal in itself. And in addition, it was very interesting to get more information on the noise according to the heat pump operation, and it's useful to be used as input for the other tasks. So the first task was to select the heat pumps for this round-robin test. You can see some figure from European markets, and for the air-to-water, water-to-water, air-to-air, and heat pump water heaters. And you can see that the distribution over the different countries are very various. Many air-to-air in Denmark, Italy, or many air-to-water to Austria and Deutschland, and more to heat pump water heaters for France. So at the end, we decided to have 3 round-robin tests, RT1, RT3, RT4, over the main part. And for this presentation, I focus on the results from RT1. Some words about the standards relative to heat pumps. And for the capacity characterization, there is the EN14511 series, especially the part 2 with test conditions, very important for the labs. And also the EN14825 for the part load condition and the calculation of seasonal performance. For the acoustic, because it's Annex dedicated to the signature acoustic signature of heat pumps. It's the standard to apply the EN12102-1, the determination of sound power level for the heat pumps. And more specifically, we focus on the Annex A4, which gives the requirements pertaining to eco-design and energy labeling regulation, which is quite specific operating condition. we decided about a test program and to investigate for all these capacity or operating condition. First, EN 14511, very standard operating rating condition with the air at 7 or 6 degrees and water 30-35 with some modification or variation, for example, the maximum frequency. Then we want to use the, let's say, acoustic points, EN 12102, but to perform this one, we have first to have the capacity, the measured capacity of the EN 14825.C at 7 degrees. So it's a specific operating condition and it's quite tricky to implement. And then it's also the opportunity to have part load conditions at 12, 7, 2, -7, -10 degrees. And of course, we do not only perform capacity tests, but also acoustics for all of these operating conditions, which is not so usual because accredited laboratories are used to perform in 14511 or 2102, but not so much the other for acoustics. Very various acoustic environments, pure climatic chambers, single or double, but they are used as our rooms to get a diffuse fields to apply the ISO 3743, the engineering methods, or use as free field using acoustic materials on the walls from using ISO 3744 or 3746. There is pure acoustic rooms, double reverberation room in the bottom, using laboratory measurement 3741, and in between rooms, climatic rooms, but adapted for designed for acoustics with this sketch. You can see some picture of the outdoor units in several environments: diffuse reverberation room, climatic room, free field room with the special dome with many microphones, and you can see the team during a visit in the in-between room, climatic and acoustic room. Give my microphone to Thomas. We cannot hear you.
Okay, can you hear me now?
Approve.
Can you hear me?
Yes, we hear you.
Okay, very good. So amongst the different types of devices which got tested in those round robins, the air-to-water device we tested was a single split. So if you don't know, this means that the different components of the refrigerant circuits are split into two parts. The indoor units typically comprehends the condenser, where the heat from the air is transmitted to the water circuit. This is not a very critically loud part of the device, so it did not get investigated regarding acoustic signature. We focused on the outdoor unit, which typically features the fan, the compressor, and all other components which can come to loud noises, transient noise like valves and so on. So this heat pump was a 10 kilowatt heat pump, and it's got measured and circulated amongst laboratories across the European partners for this annex. So as explained, the one main goal of this round robin test is to ensure that the measuring standards and the way it's implemented in the different laboratories with their different measurement techniques are in good agreement. This you can see at the example of this measuring point with an air temperature of 7 degrees and water temperature of 35. This plot represents the whole spectrum of the overall sound power level. Each color of plot represents one laboratory which took part to the measurement. And as you can see, there is a very good agreement with an overall variation of the sound power level of maximum 1.5 dBA. Then, having ensured the good agreement of the measurements between laboratories, the focus comes to the influence of components, because I repeat, the main problematic of this topic is to try to assess the variations of noise level depending on the operating conditions, that is the external temperatures, the load of the device. And for this, of course, the more load or the coldest the air outside, the more the heat pump has to work hard. And this in turn leads to faster spinning fans or compressor. As you can see here, with the same speed fan, the two blue curves represent two different compressor speeds. And you can see that the light blue curve representing a faster compressor speed is slightly louder. Now, yes, okay. The red curve on top is the measurement of the the standard 15511. And it's interesting to note here that at this specific fan and compressor frequency, we get some resonant frequencies for the third octave bands of 300 Hertz and 800 Hertz. So this means the evolution of the noise level is not necessarily always increasing regularly across the whole spectrum. It is possible that some operating points of the heat pumps just trigger some resonance frequencies, meaning the structure comes into resonance with the source excitation of the compressor or the fan, typically. Now, having a look at other curves where the compressor runs at the same speed, but the fan speed varies, it's easy to notice that the hub, the gap between the different noise levels across the whole spectrum, is much more predominantly dependent on the fan speed, with variations of almost 20 dBs depending on the fan speed. So for this device, the fan is the predominant source, noise source. This, with those few data points, this can be illustrated on the plot you can see on the right, where you will notice it tends to indicate a linear evolution of the global sound power level depending on the fan speed for this device. This is not always the case. At the example of a previous study that got conducted internally in Fraunhofer, you can see that another air-to-water heat pump displayed a predominantly compressor-driven global sound power level. On the left, the plots indicate the different spectra for different compressor frequencies. And with even more operation points measured, you see the tendency to a linear evolution of the sound power level in dBA, depending on the compressor operating frequency. This normal highlights the critical importance of being able to assess which component is the predominant source depending on the device. And this is actually what gets developed as a methodology for measurement internally in Fraunhofer. Now, this slide is here to show that we got measurements under all standard conditions. Here you can see on the plot the various part load conditions of the standard EN 14825, where the only varying parameter with the same temperature gap between like the same water temperature gap, the only varying parameter is then the ambient air temperature. And without surprise, the colder the air, the harder the heat pump has to work. You can still notice that up to a certain temperature, air temperature, the heat pump is anyway getting near to its maximal operation frequency, and the curves then tend to overlap themselves without big changes anymore. Now the green line that gets on the plot additionally represents the standard, the acoustic standard. As François said, this condition operation is quite tricky to implement, and on top of that, you can see that it doesn't really help to represent the potential level of the sound power of the global heat pump. It tends to be too low to really represent how loud the heat pump can get. Now we find again the curve of the EN14511 with resonant peaks, and it is to be noted that, on the contrary, this measurement points seems to reasonably represent the highest level the heat pump can reach, but without being the absolute maximum, but rather closer to what the average operation conditions can lead to. This is a preliminary information which leads us to consider, is there a possibility to express how loud a unit will get with only a few sound power levels, or even only one? And this is what François will try to investigate in the next part.
Okay. So now we have all data to perform something that we could call seasonal sound power level, inspired by the seasonal coefficient of performance from EN 14825. We have climate, average climate between -10 and 15 degrees, and almost 5,000 hours of operation distributed among the temperature. And you can see the 4 target temperature at -7, 2 degrees, 7 degrees, and 12 degrees, for which we have results in acoustics now, which is rarely the case. So the calculation to implement is a quite simple average, weighted average, log average of the different sound levels, weighted by the duration of operation occurrence. This calculation is done like that. First, you have the results of measurements in the arrows. Between these values, we do a linear interpolation, and below -7 and above 12 degrees, we remain the values constant. And then we have just to weight this sound level by the number of hours of occurrence for each. And we have here a relative contribution of each. And when you sum, of course, a logarithmic sum of all these contributions, find the result, which is 62 dBA for this seasonal sound power level. You can see that here are the most contributing part of the results, around 2 or 1 or 2 degrees. And if you calculate only with these values, you are not exactly 66, but almost 64 or 65. So the main part of the information is in this area. We have to take into account, for a better result, we take into account the intermittent work of the units. And first of all, it's a frosting, which appears for lowest temperature. And we observed that during the frosting, average sound level, which is during this very small interpeak, it's almost 15 dB lower than the normal operation. And during this defrosting, there is many noise events. And if we make the calculation, it's, yes, we can calculate it's almost 15 dB below. About the duration of defrosting for this unit, it was 5 to 6 minutes every 80 to 130 minutes, but it depends on the temperature. So we make some assumption of what could be the time of defrosting according to the temperature. We put these values, it's assumption, but we'll see it's not very important. Another way for the units to be intermittent, it's when the temperature becomes high, above 12 degrees, the load is low and the heat pump works intermittently. In the same way, we make some assumption of what time it could be stopped during this phase. So this is the improved calculation. You recognize the same values here, but here we added some information related to defrost and to time stopped when cycling. We took this value of 55 dB for during defrost and 0 dB during stopped. And here you have the contribution, relative contribution of this special operation. And to be fast, the result is only 60 dB, only 0.2 dB less than previously. So it doesn't change not much. And here you can see that there is very small contribution to the result. So the main contribution remains in this area around 2 degrees. Finally, we can ask which metric could describe the heat pump sound level. Here in this table, you have the result of the 4 labs which perform all the program, and is here in the average. You can see the seasonal sound level in average 64.8. If we compare to the usually used operating condition EN 12102, we can see that, as said Thomas, this is quite low because the load of the unit is quite low for this condition. So it seems to be not so representative of the operation of the units, and to give a single value, which is this one, for example, seems to be not very representative. And as he said, the operation condition is very tricky to set. And consider also the EN 14511 as a result. And you can see that it's closer to the seasonal sound power level in average less than 3 dB. Very seducing condition because it's very easy to implement for all labs. Just usual to do that. And in addition, it's very close to the partial load point B at 2 degrees. And I said that 2 degrees was a center of gravity of this for seasonal sound power level. So it seems to be a good operation condition, but of course it's not declared right now in the European regulation. So is the problem. So I think that this table gives the information, figures, and that we didn't have, especially the seasonal sound power level. And even if this conclusion has to be confirmed by tests on other units, I think it's a first step to have a reflection on what could be a single value to describe the sound level of a heat pump. Thank you for your attention.
Thank you very much for your presentation. And I would like to remind all the people who are listening that if you have questions regarding this presentation, please write them in the chat field and they will be answered in the end. Now I need to see, do we have Roberto Fumagalli? Would it be possible for you to present now?
You can see me?
Yeah.
You can hear?
Yeah, I can hear you.
Okay, no problem solved. Okay.
Good,
I share the presentation. Okay.
Yeah, perfect. Please go on and present.
Okay, thank you. Excuse me for inconvenient. As introduced by the chairman, my presentation will focus on the analysis of the national legislation and standard which regulates the limits and the sound emission of the heat pumps in European country. This topic was deeply analyzed within the task one. The main goal was the identification, collection, and analysis of national legislation and regulation, which limit the sound emission of heat pump based on their application and the location. And the analysis of the standards was used to determine this emission. The important aspect of this analysis was to get information and perception of the heat pump noise in different countries and to use them on a basis of possible future guidelines and standards applicable to different areas. Specifically, the study carried out with the task as regarded a brief introduction on acoustics, both physics and perception, an overview of measurement techniques, these two for non-acoustic specialists, and a collection and comparison of international measurement standard, national law, European certification scheme. For each of these topics, a deliverable was produced. In this presentation, we'll show only some results of this comparison. The data collection is not was easy because the laws are written in original language. There is not always an English translation, and above all, it's not easy to know which are the laws we are looking for. For this reason, each participant has made available all its knowledge on the topic, and also make the effort of do research on other member countries. These are the countries covered by this research. In addition, there were already data available on other countries. In particular, the data on Switzerland is important because Swiss is an important market for heat pump. The approach, the possible approach of the environmental power, the environmental laws are many. Some nations in this example divide the territory in homogeneous zone, acoustic zone. This in this picture we can see which country have this approach and an example of area, the division by area. The example is the German national territory. Another approach is to divide the period of the day in different period. Often now day and night. In some cases, also the evening is added. The evening is added after the introduction of the 202, the European Directive 202/49 that define also the evening period. In this table, we can see the data collected country by country. Not also, but every area have a limit, a different limit. In this case, we can see the maximum limit of noise admissible area by area. But most important in our case is the minimum limit area by area. The maximums refer only of industrial area. Instead, the minimum is referred to residential or other area that require a climax quiet. Okay, in this table we can see on the top the previous limit shown, and on the bottom some specific specification of introduced only by some countries, not for all. There are some specification. In example, we can see that there is an approach to divide the period in the weekday. We can take in account only in a few countries. Here we can see that many countries have the description, have its own descriptor. So there is not only the one kind of make measurement, and not only is carried out in homogeneous mode. In particular, I catch the focus on the fact of there are also some penalties, and these penalties can affect the tonal component and the tonal component in low frequency, and this is the case of heat pump. Another approach is to divide, is to consider annoyance in not considering the zone, but considering the max noise inside the home. France, for example, does not have a division by territory zone, but still provide very stringent maximum noise limit inside the home, even during the day period. Here is a brief description, the brief summary of descriptors used for building acoustic inside acoustics. And in bottom you can see also the limit, but I can recall a focus on the fact that some nations have specific limits for technological service installation as heat pump, for example. Finally, the available documents also contain a brief overview on the standard used for the evaluation of the sound power, from the generic, the ISO, to the specific, the ION 12102, that you have already seen in the presentation that was before me, the result using this annex, this standard, sorry. In conclusion, different countries have different approach. And harmonization is difficult to achieve because every country have its own law system. But instead of that, European certification scheme and regulation are today all based on EN 12102. So is the cause, because we have used this standard for the Annex study and the Annex analysis. Okay, this is the document produced, and I thank you for attention.
Thank you very much, Roberto. Now we will go on with the next presentation, and we welcome Kamal Arumugam from DTI in Denmark. Could you please share your slides?
Yes, can you hear me?
Yes, we hear you well.
Yes, good. Yes.
Could you put your slides in slideshow mode? Yes, thank you. Now it's fine. Please start your presentation.
Thank you. Yes, I am Kamal Armugam from DTI. So my title is Effect of Heat Sinks and Operation Modes on Acoustic Emissions. And all the data I'm using in this presentation are from DTA laboratory measurements. So today's domestic heat pumps are designed to handle different heating systems, such as floor heating, radiator heating, or hot water systems. This means a heat pump have to supply different water temperature. For an example, 35 degrees Celsius or 55 or even higher. So how does it affect the emitting noise level? What are the causes? So let's look at an example from an DTL laboratory measurement for an air-to-water heat pump. In this example, we only change the water temperature, that is from the inlet water temperature from 30 to 47 and the outlet temperature from 35 to 55. And we maintain the heating capacity and the outdoor temperature for 7 degrees Celsius, the outdoor temperature, we maintain this temperature. So we can better compare the result. The reason for we maintain the capacity is the most of the heat pumps today in the market, they are able to supply the heating demand as the heat sink temperature increases. So therefore we maintain the heating capacity as well. So how is it affect in the emitting sound level? As you can see, the sound power level is increased from 59 to 62. This is increased by 3 dBA. What are the reasons for this increase? As you can also see, the power input, the compressor and fan speed are increased as well. And please notice the power input. The power input is increased by 56%. This is relative high increase. The reason is, as the water temperature, as the outlet water temperature increases, the condensing pressure is also increases. This means more vibration for the heat pump. And the compressor and fan speed is also increased because it is necessary to maintain the same heating capacity as A7 water temperature 35. So let us take a close look of an noise spectrum. This is a typical noise spectrum for an air-to-water heat pump, where you can see the most dominating components is from the components such as, in the low frequency, the noise is dominated by compressor speed. But in the middle and high frequency, this is the noise is dominated by the fan speed. But in this particular example, you can see an increase of the compressor speed is also increasing the emitting noise you can see in this region, and also an increase of the fan speed also increase the emitting sound power level. So these are the reasons for increase of 3 decibel as increase of the heat sink temperature. So an increase of water temperature results in an increase of emitting noise level. But this is not desirable. In addition, it is preferred to run the heat pump with reduced noise level, for an example, during the night. Today, most of the heat pumps are supplied with operation modes, which can reduce the noise level for short time or for long time as it wanted. But the different manufacturers have given the different names for these operations modes. Some call it silent mode, others call it quiet mode, and others call it low noise operation mode. But the function is the same. All of these modes can reduce the noise level. So how does it work and what are the costs? So let us look at the same example, the example for the same heat pump as before. But in this example, we maintain the water temperature, as you can see here. Inlet and outlet is same, 47, 55 is the same. And we maintain also the output temperature and activates the silence mode. So how is it affect the sound noise level? Yes, this give a reduction of 5 decibel. The sound is reduced from 62 dBA to 57 dBA. This is a good reduction. What are the reasons for this? As you can see, the power input, the compressor, and the fan speed are reduced as well. So take a close look at noise spectrum for this measurement. But for this operating condition, the fan speed and the compressor speed are reduced relative high. So you can see the reduction by reducing the reduction of fan speed is pretty much, which is the main contributor for the reduction of the 5 dBA. But by some cases, for some reasons, the reduction of the compressor speed not contribute for the reduction of the emitting sound, in particular in this specific measurement. So there are places to improvement of this operating conditions, operating modes, yes. So in fact, in this case, the heat pump is running in part load condition, but the control strategies are not necessarily the same as silent mode, because for the silent mode, because for the part load condition, the heating demands and the efficiency are on focus. And it can be done adjusting the compressor speed only. But for the silent mode, the emitting noise level is on focus, and it requires an optimal adjustment of the compressor and the fan speed. So thank you for your attention.
Thank you very much, Kamal, for your presentation. Now we welcome Tore Oltersdorf from ISE in Germany to make his presentation. Could you please share your screen, Tore?
Yes. Can you see it?
Yes, it looks fine. Please start.
So hello, everyone. Thank you for your time and for your attention. I will present you today the activities we had in the task 4 and partially in task 3. Unfortunately, we have not so many experiments we can present in these tasks because we were focusing on gathering information about transient noises, operating conditions, and noise control strategies that could be applied to heat pumps. Just a moment. So I want to start with showing the interdependency you have for air and structure-borne noise. So that means I will focus on the type of air-to-water heat pumps. So you have the heat pump system, which is mainly including the excitators of the compressor and the fan. These are your, they can be your primary sources for acoustic emissions. And then you have secondary sources, which could be heat exchangers and valves. And you have the unit noise, which would add up to the final heat pump you see at the end. Air is, for the air-to-water heat pump, the main medium, which contributes to the emission of sound. And this is mainly recognized as an emitter. The emission of noise is through the inlet and the outlet of the air. Additionally, you could have, but this is a minor source, that the air can excitate the casing. And of course, when you have the heat exchangers inside the airflow, they also can contribute to the noise generation, for example, due to the pressure drop you have in it. And the valves also can contribute as secondary sources to the noise emission of the seen by the air flow. The flow acoustics is not only available by the air, it's also the refrigerant itself. The refrigerant flows through the valves, it flows through the heat exchangers, and to finalize the circuit or to complete the circuit, it also flows in between the heat exchanger and the valves. And all of this will have some flow acoustics and could finally be any kind of noise that is emitted to the airflow so that you can hear it. Then you have structure-borne noise. The structure-borne noise comes from your excitators, and the structure-borne noise is excitating the casing, but either directly when you don't have a lot of suspensions, but when you have suspensions, first suspensions are excitated and then the casing by being connected to the suspensions. You also have structure-borne noise that will excitate the heat exchangers, structure-borne noise between the heat exchanger and the valves. And actually this sums up to almost all, I would say 95% or 98% of all interdependencies are now shown here. There are some minor interdependencies, but these are quantifying to most of the noise emission contributions you have. So now you have a black box having all information in the heat pump, and then you have kind of exterior airborne noise emissions, or you can have exterior structure-borne noise emissions, depending on the installation location where you have your heat pump. I have not shown here the flow acoustics of the hydronic circuit. This, for example, is the part where some other noise emissions would come from. So then you have kind of an absorption process when you install, for example, insulation materials. You have kind of a radiation process when you have at first structure-borne noise which emits inside the system and is excitating the casing before it excitates the external envelope of the heat pump, which would result into exterior airborne noise emissions. So now I would like to say some words to the task 3 activities, which contributed a lot to identify the noise, which is characterized by some by its components of a heat pump, and especially for the noise control which you could have to reduce the noise emissions of your heat pump. One of your first steps would be to have your primary sources and try to silence them, for example, by put suspensions to the feet, to the mounting points of your compressor and your fan, but also to put some envelopes around these source excitators you have in your system. There are some other noise control measures you could take, as I said already, putting insulation material into your casing, for example. You should, now you see 3 different cases of noise control. You have the silencing sources for your primary sources, you have the noise control inside your heat pump, and you have kind of a noise management outside, what means that you have a look, that you need to have a look for the installation location, and that needs to be matching your needs to have a low noise heat pump as well. So then you have some other possibilities. You could put silencers around the airflow to make it quieter. And yeah, as I said already, the insulation material. I will focus in the next 2 slides, 3 slides, on the transient noise effects you could have in operated heat pumps. There's on the one side, as I said, I focus on the air-to-water heat pump. In the task 4 report, you will also find some words on brine-to-water heat pumps or hydronic heat pumps. But in the air-to-water heat pump, transient noise conditions are valid when you have operating conditions usually lower than 7 degrees Celsius ambient temperature. And then you have this interaction between frosting and defrosting, what means to reverse your cycle, and you will have kind of tonal noises, as we heard already in the report on the task 2 activities from François and Thomas. Then you have on and off versus modulation of the compressor or the fan, which could be also a transient noise, could result into transient noise effects in the operated heat pumps. There are some more. For example, the domestic hot water tapping can result into acoustic emissions, but these are not shown here as well. So transient noise effects in operated heat pump, we tried to make a survey. What are these effects? So your dynamic processes are frost growth, defrosting, superheat control, compressor frequency modulation, hydronic pumps, hydraulic valves, airflow, or the fan frequency of the motor of the fan. You can see here just a qualitative survey what acoustic impact these different processes would have into a heat pump. As we have seen on the slide before, frosting and defrosting plays an important role in the air-to-water heat pump. And the other thing is that emitted noises strongly depend on the operating conditions you have in the system. And I would like to refer to the reports for you to have a look in there for it. The most prominent, as I said, are frosting and defrosting. So we have here one time series data where you can see the results taken at AIT. On the upper diagram, you can see the development of the climate chamber temperatures. In the second graph, you have a look on the sound power level. Third is the power of the system, and fourth is the temperature in an outlet. And as you can see, as soon as the defrosting starts, the chamber temperatures are not so easy to handle due to the fact that you have a reverse cycle and heat is put into the climate chamber, so that you need to cool down instantaneously against it. And very similar, as we have seen in the slides from François, you see that the overall, the absolute level of the sound power is of course, decreased compared to the normal operation when you have a defrosting cycle. But with all the peaks in between, you see that you have kind of a tonality during this this operation mode. Yeah. So I would like to conclude with one slide on on some how to say on how to quantify, for example, what the compressor brings up for the whole noise emission, and how all the shares the compressor is contributing could be quantified. I go back to the same flow scheme you have seen before several times, and actually this is kind of an unclarified issue right now, and not completely clarified with Annex 52.4, but we would like to put your attention a bit on these things too. So for example, when you have air, you have the compressor. I just focus on the compressor. I don't say now something on the fans, because I assume that you are using already acoustically optimized fans in your system, and then the compressor could become louder than the fan. And now is the question: what is the share of noise emissions from the primary source? What is the share of flow acoustics by the refrigerant circuit, which is connected to the compressor? And what is the share for the structure? So, and even here, for the structure, you could still have some kind of direct emissions, structure-borne noise transfer paths to the heat exchanger and the valves, which is then indirectly interacting with the casing as well. But you also can have direct interacting with the casing. So it is not so easy, finally, to say here in some concluding words how much it is, because this is part of running research and very interesting to see. And I suppose that this is going on after Annex 51 is closed. Thank you very much for your attention.
Thank you very much for your presentation, Tore. We will go on with the next presentation from Christoph Reichel from AIT in Austria. So could you please, you stop sharing, and we'll let...
yeah, okay.
Yeah, and Christoph, please share your slides.
So,
yes,
I hope
thank
this
you. Now
time it's working.
Yeah, we'll see you then.
As I'm looking at the clock, I will speed up a little bit so that we have enough time for some questions. You can always have a look on the documents. So heat pump installation effects on surrounding environment. I want to bring your attention to some points. It's about, first of all, tools which are used for calculating sound pressure levels. I will speak a little bit about virtual placement of heat pumps, the analysis of acoustic interaction of multiple heat pumps, and some additional topics. So first of all, heat pump placement and effect on surrounding environment. So you find the documentation as discussed before on the website of Annex 51, and you can download them and have a look, and some details we will present here. And the first of all is, what can you find for tools for calculating the sound pressure level? And first of all, you can find simple web-based calculation tools on the internet. I have given here 3 examples. It's from Germany, Austria, and Switzerland. So it's simple tools. They are web-based. They use simple formulas, and you can calculate the sound pressure level at a point when you have the sound power level of the unit and the distance to the unit. And if you want to see it a little bit more in detail about a 2D visualization, and you see more about the propagation, you can use this tool, for example, which is available in Denmark, but you can also use it with addresses of other countries, which I've shown here. So it's a 2-dimensional tool relying on the same formulas we saw before, but you can visualize it a little bit. So you can place your heat pump. This is at our place. So just bring it somewhere and you see the propagation. But of course, without absorption, reflection, or frequency dependencies. What you can have in these tools is some sort of corner and wall placement penalties. This is normally included, but if you want to have more, you have a much larger computational effort. And therefore, there are advanced sound propagation tools available on the market, both commercial and free. So Kettner A, SoundPlan, Noise3D, Mitra, IMI, Olive Tree, LabSuite, OpenPSTD. And you can play around with these ones, but you can also go to a full three-dimensional calculation of sound propagation using boundary or finite element method. And that brings me to the next point, to the virtual placement of heat pumps. And what we are doing here, and we have discussed this also in our Annex quite a long time, is we want to give an option to use 3D tools and virtual and augmented reality, so your normal mobile device, to visualize the sound and to make your heat pump hearable and audible. And what we are using for measurements normally is this acoustic dome, which is quite detailed information, but we can also go here on the left side to something like a 5-channel measurement, which is quite simple, only placing microphones at the 4 sides and on the top. And we use these measurements for the whole transient part of the measurement, so that we can capture all the transient effects and also wave files, which we can use for making the heat pump hearable and audible in the applications. And here you can see one glimpse of such an application where a virtual heat pump is put in your real environment. So using your handheld device, where you can look at your building and you place your heat pump, and then you can visualize the sound propagation. And in the first step, it's also relying on these simple calculation methods. But with these devices getting better and better and hardware getting faster and faster, we can implement here a lot of nice tools and nice mathematics, so that we can even capture walls and work with absorption reflection. You can download these things for testing. It's free. You can try around with these maybe options how we in future will work with visualization. Next part will be how to work if we have multiple heat pumps. And we did a research here with one of the commercially available tools. In that case, it was IMI. You can download the full work, which was done from a student and in supervision of AIT. In the download section, what we wanted to do here is, this was a new building area, a terraced area where we have new buildings built. So these are these houses in red, and there are some houses which will be built in the future, which are in blue, and some heat pumps which are in orange, and they are the sound source, of course. And the emission points are quite a lot in this case. So we have listed all the building doors and windows, and tried to question now, so what we will hear at all these emission points, and what can we do with our heat pumps? And what we came up was a simple solution to say, okay, if we have a look on our emission points, which you can see here on the y axis, and you look at different variants, and you add penalty points for each dB which you are above the limit which you can set freely, then you can see how bad or how good variants are. So we are searching more or less for a variant where the screen is completely black. So we are searching for a complete black column, because then we will never have any penalties somewhere. And if you see a very light area, then you see, okay, there a lot of noise is there, and then you can search for best solutions. You can also try to include noise barriers to look which heat pumps should be covered by a noise barrier, which heat pumps you could use. Maybe you use not only one type of heat pump, and you can look for the sound pass, and you can even have a look on time of the day simulation. So in that case, we looked for all the buildings, we came up with different user profiles and added them in. If you are more interested into this, then just please download the document and have a look, and just write emails if you have questions for that. And this brings me to the last point. So what you also will find in the document would be analysis of unit placement and indoor-outdoor sound propagation. You would find some tools, information about the potential of sound absorption at nearby surfaces, and some discussions about common unclever decisions in heat pump placement, and a link for some further placement data. This was quite fast now. To summarize, task 5, the deliverable of task 5, the report on heat pump installation, with special focus on acoustic impact. Impact is available for download already in version 2 now from the Annex website. We have simple web-based calculation tools visited. I have shown you some two-dimensional visualization tools, and we also have a look on augmented reality, maybe a next step in having a look onto acoustics and make your heat pump hearable. You can download and test it. And we had a look on these investigations of the placement of multiple heat pumps using a commercial tool. And so with that, I will go out of the stream here again and go back to Caroline.
So thank you very much for your presentation, Christoph. We will now welcome our last presenter, Henrik Hellgren from RISE, who will talk about annoyance rating and psychoacoustical analysis of heat pump sound. So please, Henrik, could you share your slides with us?
Of course. Fine.
Fine, everything looks fine. So please start your presentation.
Okay, so my name is Henrik Hellgren. I work at the Research Institute of Sweden in Borås. I will present some preliminary results that are linked to the annoyance rating and psychoacoustical analysis of heat pump sound. So we have uploaded a draft report to the webpage, which includes some more detailed information, of course, of the experiments. At the moment, these are preliminary results, and it will be updated before the end of the year due to some delay in the experiments due to the COVID-19 situation. And I also note that some introductory overview is available in the documents presented by Roberto. In this report, at the moment includes 2 investigations. I will focus on the one where we use the free magnitude estimation with sounds from an air source outdoor unit. And we made this experiment with an Austrian and a Swedish listening panel. So RISE, together with the Austrian Academy of Science, the Austrian Research Institute. So for these experiments, we made recordings in a hemiachoic room, and we made the recordings in 4 microphone positions. You can see the setup to the right. So in the front, right, back, and the left. And also in 4 operating conditions. And during the experiments, the listening level was equalized or normalized to 40 dBA to link to the legislation for example, for the neighboring property. So some results from the annoyance rating. These 2 graphs essentially show the same thing, but are ordered. The left one is ordered with the condition, and the right is ordered with the microphone position. And here to the right, you can see what fan speed and compressor speed was measured during the recordings, and we can see that the condition denoted low is is rated more annoying. And we also see that the right position is on the compressor side is rated higher. And this is what we also see here with the low condition is rated higher, and the right position is seem to be more annoying. So the psychoacoustical quantities can be useful to describe the character of the sound. Usually we use the dBA, the A-weighted sound power level, to describe the sound for legislation. But the psychoacoustical quantities can describe the character in a better way. And the common quantities could be loudness, sharpness, roughness, and tonality. And if we look at, for example, loudness, sharpness, and roughness, we can see that for the different conditions, that the different positions or have emphasis on these different sensations, you can say. So, for example, the roughness is increased in for some conditions, and the sharpness is higher for in this graph the back position. And this is also the same quantities, but denoted with the microphone position. So here we can see the right position is differs from the other positions, and yeah, you see this also for the roughness. So then we have some annoyance rating, and then we have the psychoacoustical quantities, and then we can try to make some kind of annoyance index. And this can be done by some regression model, and in this case, a stepwise regression model. And the output of this is that the single best descriptor is the roughness. And if we look at this R squared, we can see that this explains about 40% of the variance. So although it's the best descriptor, it doesn't entirely explain how you rate the annoyance. And if we add sharpness to the model, we get up to around 60%. So this model explains about 60% of the variance. And then you can go on and add more quantities. And then you can get, if you add also loudness and the tonality, you get the model that can explain about 94% of the variance. So in the end, you have to decide what kind of do you want to reach 100%, or are you satisfied with less? But if you add more, you the quantities can explain more of the annoyance rating. But we can see that this is a quite complex relation. So you have to understand that the sensation linked to the annoyance can be quite a complex relation. And that's the, I think I'll stop here for a moment, so we have time left. And please have a look at the updated version if you're interested with these results.
Okay, thank you very much for your presentation, Henrik. We will now go over to Q&A session here. And actually, we have not received very many questions during the webinar, but we have one question here, and it's to you, Henrik. And that is, does condition correspond to load on the heat pump? So does it correspond to outdoor temperature, for example? Could you please answer that question?
The temperature is kept constant during the recordings. So we haven't really quantified the load, but we just adjusted the setting of this was an air-to-air machine, so we adjusted the indoor fan speed to vary the condition.
Okay, thank you very much for your answer. Our plan here was to have the questions written in the chat field, but since we have not received that many questions, I open the floor. So if anyone in the audience want to pose a question now, it's okay. So please. Okay, I received one more question. It says I will check here. Just a minute. Ulrika, maybe you could read the questions because I cannot really see it right now. Could you do that for me, please?
Yes.
Yes.
How can the results be used to improve the EN 12102? Did I get it right?
Yes. I think it's not at the place of TC 113 working group 9 to decide. The standard 12102 is only a way to make the measurements and to installation of heat pumps. When I speak about Annex A4, it's to be in line with the recommendation, the requirements of European Commission. So I think it's not at the level of the standard to decide that, but a higher level of declaration or labeling, etc.
Okay, thank you very much. And I think the time is soon out, but I think we have room for one more question. So if any one of you have a question, please come forward and pose it. Okay, I cannot see that we have any more questions right now, and the time for the webinar has come to the end. So I will finalize here by thank all of the presenters who held the presentation for all the information they shared between us. and for all you who attended this webinar, that you did so. And as we said, all the presentations and the recording of the webinar will be available on the HBT Annex 51 website. So thank you everyone for today.